Hi, my name is Justine Harkness, and in this video, we'll look at how to predict the products of an anti-addition. During an anti-addition, groups will be added to opposite sides of a pi bond. So let's take a look at an example. Here we're starting with an alkene, and we'll add some sort of a reagent that undergoes an anti-addition to get our final product. Now, in this anti-addition, notice that our two groups have added to opposite sides of the molecule. We can further show this by drawing a Newman projection. So we're going to look down this carbon-carbon bond, and we'll start with our first carbon that we see. So our first carbon has that new substituent at the top, and we'll have the two hydrogens at the bottom. Looking at our back carbon, of course, we denote that with a circle. We see our new substituent is now on the bottom, and then our two hydrogens are along the top. So in this Newman projection, we can again visualize that our substituents have been added to opposite sides of our molecule. Now let's come back to look at some other interesting properties of this reaction. Now, we had labeled these two hydrogens in a lighter blue to show how their orientation changes during the course of this reaction. These two hydrogens on light blue are currently on opposite sides of this double bond. And notice that after the addition reaction, these two hydrogens are on opposite sides of the molecule. So during anti-additions, we don't change the relative positions of substituents about a double bond. If they're on opposite sides of a double bond before the reaction, they'll be on opposite sides of the molecule after the reaction. And if they're on the same side of the double bond before the reaction, they'll be on the same side of the molecule after the reaction. Additionally, just like with all other types of addition reactions, we see a decrease in the bond order. We're starting out with two bonds between our two carbons. This would be a second order bond. And then after the reaction, we only have one bond between our carbons. So this would be a first order bond. So again, we see that decrease in the bond order with a subsequent increase in the number of substituents. So let's take a look at a few different reactions that you will see or have seen during your tenure in organic chemistry. So in our first example, we see halogenation of an alkene creates an alkane through the anti-addition of two halogens. And we want to know what the product of this reaction will be. Now, looking at our reactant, we see that we have our two methyl groups on opposite sides of the double bond. So we're starting with the trans alkene. And if our groups are on opposite sides of the double bond before the reaction, they must be on opposite sides of the molecule after the reaction. So we can draw our first methyl group on our left carbon as coming out of the page, and we can draw the second methyl on the other carbon as going into the page. Now, since this is a halogenation reaction, we're adding two bromines, and we'll be adding one bromine to each carbon, and they'll be adding to opposite sides of the molecule since this is in fact an anti-addition. And finally, we'd be left with those hydrogens which were implied in the reactant, but we can draw them in the product. So they are on opposite sides of the double bond before the reaction. So notice again, they'll be on opposite sides of the molecule after the reaction. Now let's take a look at another reaction type, and this is going to be a hydrogenation reaction. So this question is telling us that we have an alkyne being reduced to a transalkene through the addition of two hydrogens. So since we are adding hydrogens to a pi bond, this would be another example of a hydrogenation reaction. Now, to predict the product of this reaction, we actually need to use some information from the question stem. The question stem tells us that we are producing a transalkene. So remember that transalkenes have alkyl substituents on opposite sides of the double bond. If we were to look at each carbon in this triple bond, each carbon has a bond to an ethyl group here. So in our trans product, we would want to have each ethyl group attached to opposite sides of the double bond. And in order to get the ethyl groups on opposite sides of the double bond, we would have to add hydrogens to opposite sides. So through the addition of hydrogens, we're able to get that trans product, which tells us that the addition of hydrogens must have occurred via an anti-addition pathway.